Welcome to Hart und Trocken. My name is Dirk Schiebon, and in this video I want to talk about inverse functions. And I also want to talk about how we can find the derivative of inverse functions without even knowing the formula for the inverse function. That trick is very useful in situations where we can't find expressions for the inverse functions. And that is already the case, for instance, if the original function is a polynomial, for example. So enjoy the movie and let's go. So we are talking about differentiating the inverse. By inverse, I mean the inverse function of a given function. By knowing the derivative of this given function, we will be able to calculate the derivative of the inverse function without even knowing this inverse function. To begin, let's refresh our knowledge about inverse functions. Let's start with this given function f, which is the natural logarithm, by the way. Being a function, f takes values from the x-axis and throws them on values on the y-axis. Now, the inverse function inverts this process. That means it takes the values from the y-axis and throws them back onto their original values on the x-axis. If we want to draw the graph of this inverse function into this coordinate system, we have to sort of swap the roles of the y and the x-axis, because the convention is that graphs always take values from the x-axis and throw them onto the y-axis, and never the other way around. Let me show you what I mean. At first, I draw the graph of the inverse function of f. We call it f to the power of -1. Now, as you maybe are already able to tell, the inverse function is nothing else than the reflection of the original function at the first bisector, which is this line. The reason for this relationship between f and its inverse function will hopefully become clear when we follow along what happens to some value here at the x-axis. So let's fix some point A on the x-axis. Now at first we let f throw A onto the y-axis, giving us the value f of A. Let's illustrate this journey of A using arrows. In the next step, we simply want to throw back f of A onto A using the inverse function. However, as input values for functions always have to be on the x-axis, we need to place f of A onto the x-axis. Doing this, we see that there's also a reflection along the first bisector involved. Now we are ready to apply the inverse function f to the power of -1 to this value f of A. As you can see, this gives us the value f to the power of -1 of f of A. And because f and f to the power of -1 are inverse functions of each other, this is nothing else than the point A, and you can see the distance here and the distance of the point A are the same. And this relationship stays valid if we change the position of A. Now, not all functions have an inverse function, like this function f does. In order to have an inverse function, one important condition must be satisfied, and that is that each value on the y-axis, which is a function value of f, is the function value of only one unique A on the x-axis. In other words, it must not be the case that two or more values along the x-axis are thrown onto the same point on the y-axis by f. Such a property of a function is called injective. In most cases, injectivity is guaranteed when a function is either monotonically increasing, like f, or monotonically decreasing. To illustrate this, let's have a look at a function which is not monotonic. Such a simple example is f of x equals x squared, the normal parabola. Obviously, it is monotonically decreasing in this area and monotonically increasing in this area. If we choose a value along the y-axis, there are two original values, -a and a, which are taken to f of a. In other words, the function f is not injective. Now, if we try to build the graph of the inverse function By reflecting the graph of f at the first bisector, just as we did it with our example before, we will get this. This, however, is not a function, because each value along the x-axis gets assigned one value above the x-axis and one value below the x-axis. So that is not a function. However, we can remedy the situation by only constructing the inverse functions for those sections of the domain of f where f is monotonic. So on that right-hand side, f is monotonically increasing, and on that left-hand side, f is monotonically decreasing. And in fact, this is the inverse function of this right part of f, and this is the inverse function of this left part of f. So each part has an inverse function for itself, but the complete function f does not have a global inverse function. Now that we have refreshed our knowledge about inverse functions, let's get back to our original story, how to differentiate the inverse function. Let's suppose that we have a function f which takes numbers from its domain df to its range R of f. Both d of f and R of f are subsets of or equal to the real numbers. Now let's also suppose that we have an inverse function of f which we call g, or f to the power of -1. And this takes values from the range of f back to the domain of f. Now let's suppose that we know the derivative f prime of f. What we don't know is the derivative g prime of g. Now you could say, well, that's not a problem, we just take g and differentiate it. The answer is that we sometimes just don't know g. That means that we sometimes don't have a formula for g, even though we have a formula for f. In such cases, there is a way to find the derivative of g anyway, without knowing g. We will first have a look on how that is done on a formal level, and will later illustrate that graphically. In fact, the mechanism behind differentiating the inverse is a very beautiful application of the chain rule for differentiation. Let me first write down the very equation which defines the relationship between f and g. And that is that g of f of x equals, well, x. That is just the formal way to say that x is thrown by f onto f of x, which is, in turn, thrown by g back onto x. In the next step, we consider each side of this equation as a function which depends on x. And as these two functions are equal, their derivatives must be equal as well. That means we take the derivative with respect to x of each side of the equation. The right-hand side is very easy, because the derivative of the function x is simply 1. But what should we do with the left-hand side? Well, apparently that is a composite function, and we need to apply the chain rule for differentiating it. Now, the chain rule is the outer derivative times the inner derivative, that is, g prime at the point f of x times f prime of x. Now, maybe you feel a little strange, because I just said before that we don't know the derivative of g, and in the next moment I just write it down as part of the chain rule. But that is perfectly okay, because I just write it down formally, acknowledging its existence, even though I might not be able to know the formula for it. Well, we rather use this equation to squeeze out some knowledge about the derivative of g, by simply solving for it. So if I divide the equation by f prime of x, we get g prime f of x equals 1 over f prime of x. And this is a valuable formula, because it helps us to calculate the derivative of g at the point f of x, which is 1 over f prime of x. And if you prefer that we calculate g prime of x not at f of x, but rather directly at, say, y, we simply replace f of x by y, and consequently replace x by f to the power of -1 of y, which of course equals g of y. So if we put all together, we get this formula. Now let's see how we can understand that formula graphically. So let's look at the same example as before, f of x equals ln x. The inverse function in this case is g of x equals e to the power of x. We fix some point A on the x-axis and mark the corresponding point on the graph of f. This point has the coordinates a, f of a. If we now mirror this point at the first bisector, we get this point. The coordinates of this mirror point are just the coordinates of the original point interchanged. That means f of a, a. Now we want to look at the derivative of f at a, f of a. It is represented by the slope of the tangent line at f at a. In order to represent the slope, we draw the slope triangle. Then the derivative of f at a is given by the quotient of the length of the vertical leg and the length of the horizontal leg of the slope triangle. Its concrete value is 0.33. So because the orange curve is the reflection of the blue curve at the first bisector, we can also reflect everything else like the tangent and the slope triangle. And now we have reached the main point. Because if we now want to calculate the derivative of the orange function, that means of the inverse function, at the mirror point f of a, we need to calculate the slope of the tangent using this slope triangle. However, that orange slope triangle is just the mirror image of the blue slope triangle, and that means that the lengths of the sides are just interchanged. So the derivative of g, which is the quotient of the length of the orange triangle, is just the inverse of the quotient calculated in the blue triangle. In other words, the derivatives of our 2 points are just inverse values to each other. So let us verify in this example that this is the case. We calculate for the derivative of the orange function g prime at f of a equals 1 over f prime at a, which is 1 over 0.33, and indeed that is 3. So that means we have graphically recovered the formula we have found in our earlier calculations based upon the chain rule. That formula is of course also true for other values of a. Now let's see how that formula can be used in an example. We consider the function f of x equals x to the power of 5 plus 3 x to the power of 3 plus 6x minus 3. We first want to show that f has an inverse g. As I told you before, we can do that by checking if f is monotonically increasing or monotonically decreasing. This question can be easily answered when we look at the derivative of f. So that's our first step. We calculate the derivative of f. This is f prime of x equals 5x to the power of 4 plus 9x to the power of 2 plus 6. Now because x to the power of 4 and x to the power of 2 can only take positive values, the complete derivative cannot be smaller than 6. That means it is always strictly greater than 0. Now because the derivative is strictly greater than 0, we know that the slope of f is always strictly greater than 0, and that means that f is strictly monotonically increasing at every position x. We therefore may conclude that f has an inverse function g. Let's now say we want to find the derivative of g at some value, say 7. We suppose that we know the value of g at 7, which is in fact 1. We then can apply our formula, which is in this case g prime of 7 equals 1 over f prime of g of 7, and that is 1 over f prime of 1. Now by plugging in 1 into f prime, we find that f prime of 1 is 20. So we get the final result of 1 over 20. Using the formula for differentiating the inverse in this case where f is a polynomial is particularly useful because in these cases it is impossible to find an algebraic expression for the inverse. So that was the story about differentiating the inverse function. Thanks for watching and see you next time.